webinar of rate transient analysis, specifically the focus on RTA and the PTA pressure transient analysis integration. I'm Hisham Ali, Senior Reservoir Engineer from Egypt. So, as mentioned, this webinar is designed to highlight an overview of pressure transient analysis and its diagnostic tools and applications. Then the concept of production data analysis or modern decline analysis, specifically rate transient analysis (RTA), and the comparison between and the common features between pressure and rate transient analysis, and finally field applications. So start directly with our agenda today. The introduction to pressure and rate transient analysis, modern decline analysis, flowing material balance, and the concept of material balance time. PTA against RTA, the complete comparison and the common features between the two major data analysis techniques and typical analysis tools and diagnostic plots for RTA and field applications. So the most common introduction for all reservoir engineering applications. How does it work? So basically, as you know, the reservoir engineering, it's a branch of petroleum engineering that's concerned with the applications of fluid flow in the porous media in the subsurface petroleum or hydrocarbon reservoirs. The main objective is to achieve the ultimate economic recovery by different field applications and optimizing the recovery factor. So we have three main principles. As you know, if you have this 3D representation of an oil field, we may have onshore or offshore field, and our wells may be vertical or deviated. But in the reservoir level, we have, and the reservoir, we have reservoir scale. As you can see, or porous media scale, we have a set of rock metrics or lithology of a specific specific lithology, like maybe clastics or carbonates. In between, we have specific cement material, and in between, we have the pore spaces. In the pore spaces, we have the reservoir fluids that may be mixtures of water plus hydrocarbon. This hydrocarbon fluid may be gas or oil, or a mixture of gas and oil, and so on. So the first ever principle for all reservoir engineering application is the Darcy's law of flow rate equation to characterize the fluid movement in the porous media and the fluid flow in the porous media of the reservoir. Second principle is the material balance or the continuity equation. At a specific time, the remaining volume will be the initial volume or the stored, the initial hydrocarbon in place minus the produced volume or the cumulative production. The last principle, as reservoir fluid properties like oil density, oil viscosity, oil formation volume factor, and so on, are typically functions of pressure. So as the pressure declines from the average reservoir pressure to bottom hole pressure, and then to wellhead pressure, and so on. So we have to have a specific BVT model or equation of state model to characterize fluid movement while the production process. For complete and total system analysis, actually, we have to involve two additional models, IPR and VLB, inflow and outflow models for complete system analysis and production optimization. So simply, what is the pressure transient analysis or PTA? It's simply a signal is sent into the reservoir by controlled open and shutting of the well. So once you control your well, even at the surface, by a specific sequence of the test, so we will send a signal into to the reservoir, this signal will move away in the reservoir, and in the same time will record the response of this pressure signal or pressure transient by downhole move gauges by recording bottom hole pressure versus time. So we have typically three main regions for rate or pressure trend analysis interpretation. The everyday time region, we have important data about the completion efficiency, wellbore model, and how we have wellbore storage, skin, and so on, maybe hydraulic fracturing. So this is the what we call the early time region. Middle time region, we will get more information, more description regarding the reservoir mobility or reservoir mobility, the reservoir also heterogeneity, and the type of the reservoir. And the late time region, once the pressure transient, as you can see, we have detected the reservoir boundaries. So the late time region, you will have the details of the distance and the type of this boundary. So you will have complete description for the reservoir by the interpretation of the pressure transient. So simply, the main interest of pressure transient analysis is the pressure itself. So we have to have a data acquisition and control system. So if you look at this system, we have complete system in the bottom of the well, across the well completion. You will have downhole equipment, downhole monitor gauges to record pressure and temperature versus time. On surface, we have the after the Christmas tree, and we have the choke manifold. You may have set of well testing surface equipment, the like separation system, and the transmission, and so on. So in surface, we have to have surface measurement regarding the surface flow rates and also surface pressure, up and downstream pressure, and so on. Other data like fluid sampling and the reservoir, the completion string, the details of the completion string are required for pressure transient analysis. Once we have downhole pressure data, you can analyze this data with specific workstation to for generating the complete interpretation. So in the bottom of the well, we have recorded pressure versus time. So you will have information about near wellbore effects like wellbore storage and skin, evaluation of well treatment like stimulation or the evaluation of formation damage, reservoir heterogeneity, specifically permeability, and the type of the reservoir model. And for the lead time data, you have the information regarding the reservoir boundary, reservoir shape, and accordingly the reservoir volume. And on surface, as mentioned, you will have you need to have flow rate data versus time. So simply the pressure transient analysis, we will convert the time to equivalent distance based on the reservoir fluid and rock characteristics. So applications of PTA for exploration, reservoir development, and reservoir management, simply the evaluation of average reservoir pressure, the evaluation of well completion efficiency, also determination of reservoir model and reservoir permeability, and also reservoir size or the connected volume. So simply in PTA, we will have a step function of rate, which is the input signal to the reservoir system. So according meantime by downhole recorded data, you will have measure the pressure response. So what we need to define is to define a specific mathematical model or divisivity equation to have to convert the middle model inputs or the step function of rate to equivalent model output or equivalent interpretation by matching the recorded data and matching the history of pressure and production rates. So now very important fundamentals for pressure and rate transient analysis as well as the flow regimes. So flow regimes simply are the description of the relationship between pressure and time. So the first ever flow regime is the transient or the unsteady state or infinite acting radial flow. In that case, the pressure as a function of time will be function of distance or radial distance r and time. That means the pressure will be changing at every distance and also at every point of time. In that case, we have the transient or unsteady state flow. So in the transient, the pressure transient actually hasn't reached the boundary. But once the pressure transient is reached the reservoir boundary, so we have pseudo-steady state or the boundary dominated flow. In that flow regime, the change of rate of a change of pressure with time will be constant. Partial B or delta B by dt equals constant. That means the pressure profile will be changing across the entire reservoir at the same level. So determination of reservoir volume and the reservoir size is one of the applications of pseudo-steady state flow or boundary dominated flow. Once the pressure transient reaches the all reservoir boundaries. So in that case, as mentioned, partial B over partial T equal constant. The last flow regime is the steady state flow. In that case, we assume the reservoir pressure is constant. The change of pressure with time is zero, which means the average reservoir pressure is constant. That's the case in we have a strong water aquifer or strong water influx or effective pressure maintenance system like water injection or gas injection operations. So partial B over partial T, as you can see, equals zero. So simply let's have a shut-in well in the center of circular homogeneous reservoir, as you can see. So the pressure throughout the entire reservoir is constant at BI or initial reservoir pressure, and the flow rate is zero as the well is shut-in. But we have the RW is the well pore radius and RE is the external reservoir drainage radius. Once this well is at constant flow rate like this example, so this will generate a specific pressure transient. This pressure transient, as you can see, will move in the reservoir at specific velocity or specific rate based on the reservoir work and the flow properties K phi mu CT, which means reservoir permeability, porosity, fluid viscosity, and CT or total compressibility. That means at time, as you can see, at time T1, the pressure transient will reach a distance R1, while at time T5, the transient will reach distance R5, and so on. So as long as this transient, the pressure transient doesn't reach the external drainage boundary, that means we have the transient or infinite acting radial flow, because we mathematically assume the RE or external reservoir boundary equals infinity. That's why we have the IARF, the infinite acting radial flow. Another scenario which is producing at constant BWF, but the concept is the same. So the pseudo-steady state flow and or boundary dominated flow, as mentioned, once as you can see, we have this pressure transient. If we as a transient in the green color, as you can see, so the pressure transient is still not reached the boundary of the reservoir. So we have this transient flow. The pressure rate of pressure with time function of distance and time. But once this transient, as you can see in the red color, reaches this boundary, So we have pseudo-steady state or boundary dominated flow. So the pressure throughout the entire reservoir, as you can see this pressure profile in the red color, will changing throughout or across the entire reservoir at the same level. So we can predict the average reservoir pressure by knowing the bottom of flowing pressure, and also we can predict the reservoir connected volume or the hydrocarbon initially in place. That's the concept of rate transient analysis. So this is the as mentioned, the basic mathematical model for pressure or rate transient analysis is the divisivity equation. So we, as you know, we have several assumptions for the divisivity equation, considering we have incompressible fluid, homogeneous reservoir, and so on. Darcy law is valid. But as mentioned, the basic components for this equation are Darcy's law, continuity equation, and equation of a state. But this is the general divisivity equation for radial flow. As you can see, with this term is defined, and this is the general divisivity equation in the radial form. As you know, it's a function, typically a function of pressure and time and distance r, and this is the reservoir properties phi mu ct and the reservoir permeability. If we define this term as the divisivity constant, so this is the general form of the radial divisivity equation. Let's say we have steady state flow, so this term will equal 0. So the left-hand side of this equation will equal 0. So solutions of divisivity equation simply by specifying specific initial and boundary models. So boundary conditions. So initial conditions is the reservoir is constant at 0 time, which means we have the pressure equals BI, or initial reservoir pressure. Boundary conditions, we have two conditions. The well is producing at constant flow rate, which is the basic assumption or for pressure and rate transient analysis. And second boundary condition is the RE equal infinity in case of infinite acting radial flow. So solving this equation, assign boundary and initial conditions. So we have two main approaches: constant terminal pressure and constant terminal rate. So this scenario actually, or this approach, is valid in case of water influx or water injection and so on. But the major approach applied in PTA or RTA is the constant terminal rate solution. We have two main techniques: EI function or dimensionless pressure drop solution. So this is the principle of modern PTA and RTA techniques. So you have to keep in mind the basic relationship between bottom of pressure versus time. So as mentioned, let's say we have BWF against time. So for pseudo-steady state flow or the boundary dominated flow, this relationship will be linear on the Cartesian coordinate BWF against time. But during the transient or unsteady state flow period, the relationship between BWF against log time, which is semi-log plot of BWF and time, you will have a linear relationship between BWF and log time. So this is the pressure profile at time 0. The pressure is constant at BI, and at time 1, this is the we have RI, or radius of investigation, at time T1 and time T2 and so on. This is the during the infinite acting radial flow. But once at this time we have the boundary dominated flow, or the pseudo steady state flow condition. So radius of investigation is defined using this equation. As mentioned, it's typically a function of fluid and rock properties. phi mu ct, and also the reservoir permeability, and this radius is directly proportional to the testing time. Also, we can identify the time required to reach a specific radius based on the reservoir permeability and also the fluid properties. The most important fluid property for well testing interpretation is the total compressibility and the fluid viscosity. So the concept of pressure transient or analysis is the pressure derivative, as you know. So pressure derivative is simply the slope of a semi-log plot plotted in the log coordinates and combined with the pressure difference. So simply this is the old technique is to generate the pressure difference type curves, as you can see, and but we have high uncertainty to predict the correct reservoir model because the type curves are very similar, as you can see. But introducing the pressure derivative, so we have two sets of curves, the pressure difference curves and the pressure derivative. So identification of the uniquely correct reservoir model will be more applicable and more accurate than the old technique defined by Green-Garten type curves. So the widely used approach is the border derivative, is by including the pressure difference curve, as you know, in the green color, and the pressure derivative curves. So in the during the infinite acting radial flow, we have this equation. So to calculate the derivative is dB over dt, as you can see. It will be constant and function of the reservoir permeability. So across the infinite acting radial flow, you will have this typical behavior of the pressure derivative. You will have horizontal derivative of flat line or zero slope line. This line is a function of the reservoir mobility or reservoir permeability. So we can shift this horizontal derivative up or down based on the reservoir permeability. So this is the typically the response of pressure derivative during the infinite acting radial flow period. This is the typical shape of the log plot, as you can see. We have two curves. This one is the pressure difference. Let's say we have build-up period will be BWS minus BWF at delta T equals 0. And this is curve or the pressure derivative calculated by this equation function of reservoir permeability, assuming the flow rate is constant, oil formation volume factor and fluid and oil viscosity are constant, and also net base thickness is also constant. So the only unknown for this equation is the reservoir permeability. So the concept is the pressure difference and the pressure derivative curve. As mentioned before, we have two main or three regions. Considering the early time region, we have data of well storage and this transition zone function of the skin, which is controlling the amplitude of this hump. After the early time region of well storage and skin, you will have the reservoir response or radial flow, infinite acting radial flow, defined by this horizontal derivative on the log plot. So now let's define what is the decline curve analysis. Simply, it's one of the commonly used reservoir engineering techniques that extrapolate the historical trend to predict the future performance and to estimate the EUR or estimated ultimate recovery. So we will match the past performance using a specific model, and to predict the or forecast the future, estimate the estimated ultimate recovery EUR. But we have several factors that control the decline rate, like field applications, field operations, increase in bottom of pressure in case of water injection or gas injection, and so on. So now the one of the widely used approaches or the conventional decline analysis by Arvis equation. So simply it's an empirical approach. As you can see, is the flow rate at time t function of qi, and this parameters is this hyperbolic exponent p, and the decline rate di, and the time. This is the general Arvis equation, and we have three approaches for this hyperbolic exponent. Maybe equals 0 for exponential decline, 1 for harmonic decline, and between 0 and 1 for hyperbolic decline. But you have to consider the major assumptions for this technique. We assume the well is producing at constant bottom flowing pressure, and this the Arvis equation is only available during the pseudo-state flow or boundary dominated flow. This is the basic assumption or limitation for Arvis equation. So this is the typical relationships of flow rate versus time. We have three approaches for exponential, hyperbolic, and harmonic based on the hyperbolic exponent p. But we have two common relationships to plot log q versus time. In that case, we have semi-log plot for flow rate against time in x-axis. So the exponential decline, you will have a straight line to identify the decline rate, and also if we plot the flow rate against Hume production rate against cumulative oil, also the exponential decline will generate or will exhibit as another straight line for this relationship. And that's why the exponential decline is one of the widely used techniques for decline analysis, because at specific time, as you can see for this, let's say for this time, the exponential decline will predict the lowest expected rate or the worst condition for rate prediction. So exponential decline, as it generates as a straight line, which can be defined as a CBD or constant percentage decline. So we have the flow rate or the decline rate is constant versus time. So due to the limitations of Arvis equation, because Arvis is only available, it's only applicable during the boundary dominated flow. Additionally, Arvis equation didn't account for the early time data, early production life of the well. That's why we have Vitkovich used the analytical flow equation in the dimensionless terms to the follow type curves or Vitkovich type curves that incorporates the early time data with the or the transient data with the Arvis boundary dominated data. So as you can see, this is the typical plot or typical type curves of Vitkovich. We have dimensionless rate against dimensionless time. So we have two major parts or two major regions for this sets of type curves. The transient, which is analytical based on constant BWF solution, and boundary dominated flow based on the empirical Arvis solution. So in Vitkovich type curve, we have a combination of two families of curves: the transient flow period, it's function of the early time data, or reservoir data. Late time flow period is function of boundary dominated data or reservoir volume or reservoir boundary. So we can predict skin reservoir parameters and also the reserve and how much oil on is originally in place and so on. So in modern decline analysis, we have a new definition, which is the material balance time, or what we call BNR, the pressure normalized rate. Simply, the material balance time is a parameter will convert the constant pressure solution to the equivalent constant rate solution, which is the fundamental for pressure or rate transient analysis. So let's say we have this actual trend of production data. We have actual rate decline, as you can see, against time. But if we plot if we use the next axis, the material balance time, which is the cumulative divided by the fluid. So the material balance time is the time required to produce the same cumulative, as you can see highlighted in this in the area under this curve. This is the Q capital, which is the cumulative production. So material balance time at every point will generate the equivalent cumulative if you are using the actual time. So if by using the material balance time, so the exponential curve of the Vitko beach will be equivalent to the harmonic. So this is the effect of material balance time. So this is the dimensionless rate against dimensionless time. As you can see, we have constant pressure solution, which is exponential, and constant rate solution, which is the harmonic. But by using the material balance time, as you can see, the constant pressure and the constant rate solution will be merged together. That's why this is the major principle for rate transient analysis. So the material balance time is the Q over the flow rate. And now we have this definition, which is the rate normalized as you can see, we have Q over dB, which is the pressure normalized rate. And the integral of this term will be used to reduce the fluctuation of flow rate data, which is a common issue in rate transient analysis, and also will make more data more smooth and valid for interpretation. So we have by using the derivative, let's say we have the derivative, as you can see, of this relationship Q over dB. We have this data scattered and highly noisy data. That's why you have a new definition, which is the integral derivative. As you can see, we have more smoothing in the data, which is can be valid for interpretation of rate transient analysis. So the pressure, the production data analysis, it's simply we have several categories involved, like production analysis, pressure transient analysis, rate transient analysis, or flowing material balance. So flowing material balance is actually introduced in 1995. It's an approach used to use the flowing data that like flowing pressure and flow rates to predict the hydrocarbon initially in place instead of the static material balance or the conventional material balance, because in the static material balance we have to shut in the well to have the accurate estimation of the average reservoir pressure. So, but for flowing material balance, as name implies, we can predict the hydrocarbon initially in place without shutting the well, and without need to lose production during the shutting. So this is the flowing material balance is introduced as mentioned to use the flowing data, flowing pressure and flow rate instead of instead of the conventional or static material balance. So we have two main flow regimes as mentioned before, the transient or infinite acting radial flow to predict reservoir properties, and boundary dominated flow to estimate the reservoir volume and estimate the reservoir boundaries, and accordingly we can estimate the hydrocarbon initially in place. So let's highlight what is the static material balance. As you know, it's a simple relationship between the volume, reservoir pressure, and cumulative production. Simply, the static material balance states that the total withdrawal equals total expansion of oil and also liberated gas. This is the major requirements for static material balance production data. Cumulative oil produce cumulative water, cumulative gas, and cumulative produced gas oil ratio, and also accurate estimation of the average reservoir pressure and BVT data. Applications, the main applications of static material balance is to predict the capital N and capital G stoichiometry, octangle initially in place and gas initially in place, and other applications like determination of water influx, WA, or gas cap volume. So the simplest form of static material balance is this form, the cumulative production and the stoib. It's function of the expansion of oil or oil formation volume factor, or the difference between the current oil formation volume factor and initial oil formation volume factor, or fluid expansion. This form actually, if we assume we have no water production, no gas production, no water injection, and also no gas injection. This is the simplest form of the material balance equation. So again, the flowing material balance, you can generate or you can use the material balance without the need to shut in the well during the life of this well. So we can use the flowing data, flowing pressure, and flow rates to predict the fluid initially in place, assuming we have boundary dominated flow. So, and the major approach or major concept of the boundary dominated flow is the pressure, reservoir pressure, as you can see, is changing throughout the entire reservoir at the same level. So using BWF, we can predict the BR, or average reservoir pressure. So this is the flowing material balance. During the stabilized flowing condition or boundary dominated flow, we can predict bottom hole flowing. We can predict the average reservoir pressure using bottom hole flowing pressure, and also we can use the actual production data to predict the fluid initially in place. So again, the material balance time will be used instead of the actual time to produce the cumulative production with the instantaneous flow rate. So again, this is the using the actual rate as mentioned before, actual rate decline. The material balance time will generate the same cumulative at this time, with using this in the area under this curve, which is the cumulative production at this time T1. This is the material balance time TC1 will generate same cumulative production. So for oil reservoirs, the material balance time is the ratio between NB and Q, the cumulative production divided by the oil flow rate. But for gas, actually, we will have to account for the changes, the high changes of gas compressibility and gas viscosity with pressure. So we have the material balance pseudo time, which is function of, as you can see, the mu of the gas viscosity and CT or total compressibility. So the major concept of flowing material balance is very simple, which is the compressibility equation. Simply, compressibility is the function of the relationship of rate of a change of volume with pressure relative to the initial volume. So simply, it can be function of oil formation volume factor, as you can see. So the initial volume N, so we can define the compressibility equation in terms of NV, which is the initial volume, and N, this is the volume or the remaining volume, and delta B, which is BI minus BR or average reservoir pressure. So by simple combination of previous equations with the pseudo-state equation, you will have this form, the dB over Q, which is the rate normalized, the rate normalized pressure is defined using this equation. So we have two major components of this equation. This is the first part is the pressure loss due to the depletion, and second part is the pressure loss, this one in the blue color, the pressure loss due to inflow. So this is the major difference between BI and BWF. It's a function, as mentioned, between it's function of the depletion of reservoir volume, and also function of the inflow, the completion efficiency of the well. So we have two pressure loss components, the pressure loss due to depletion defined by BI minus BR, and the pressure loss due to inflow, which is BR minus BWF. So we can rearrange this equation to have a straight line equation, as you can see, y equal ax plus b. So we can plot this relationship, as you can see, the ratio of dB over Q, which is the rate normalized pressure against time. So according to this straight line equation, you will have you have to have a straight line during the boundary dominated flow. The slope of this relationship will equal this term, and the intercept will be what we call B sub BSS, or pseudo-state constant. By also another rearrangement of this equation, we have another straight line equation, y equal ax plus b. So plotting the ratio Q relative to dB, or the pressure normalized rate against this term on x-axis. So this plot is defined as normalized rate against normalized Q. So this is the x-axis intercept, as you can see, will be the original oil in place, and y-axis intercept will be the reciprocal of pseudo-state constant. So simply, this is the pseudo-state constant defined by this equation, and this is the dB over Q, which is the reciprocal of BI, or productivity index, defined function of pseudo-state constant, as mentioned. So in flowing material balance, we will convert time. We will use time. We will convert time by using the material balance time, as mentioned, this term, and the average reservoir pressure can be defined using this equation. It's BWF plus this term function of pseudo steady state constant and the oil rate. So we can detect the average reservoir pressure using the bottom hole flowing pressure, but you have to have boundary dominated flow or pseudo steady state flow conditions. So in this exercise, we have this production history for an oil well. First, build-up period followed by this sequence of a long extended drawdown of reservoir limit test, as you can see. But actually, we have a high change in flow rate across this interval. So we plotted the rate normalized pressure. This is the actual data Q against time in hour. Plotting, as mentioned, this relationship of dB over Q against material balance time. So we have this data. So once we have a linear relationship of this linear part of this relationship, that means we have boundary dominated flow. So this part will be used to calculate a pseudo steady state constant, which is the y-axis intercept. So so accordingly, we can calculate the average reservoir pressure using BWF and pseudo steady state constant and production rate. And we can also generate this relationship Q over dB against this the normalized cumulative oil. So in this relationship, as you can see, the x-axis intercept will be the STOIB, or N. It's in this example estimated as 55.6 million stock tank barrel. Another example of a gas field, as you can see, this is the reservoir properties. So we have the flowing pressure and flow rate, and the identification of the pseudo steady state, as mentioned, using this relationship. So once you have this or part of this plot, so we can extend this straight line to have pseudo steady state constant, as you can see. Accordingly, we can calculate the average reservoir pressure using the value of pseudo steady state constant, and also we can predict the gas initially in place. And this is the prediction of gas initially in place using dynamic or flowing material balance plot, as you can see. So what is the RTA, or rate transient analysis? Simply it's an extension of pressure transient analysis using same principles, Darcy's law, the material balance and equation of a state, and we will use actually the flowing data to have description of reservoir without the need to shut in the well, like the static material balance. So we have a specific model for reservoir characterization. The applications is to predict the reservoir characteristics like permeability, accumulation efficiency or skin, and reservoir heterogeneity. And the most important part is to estimate the hydrocarbon initially in place using the boundary dominated flow conditions. So we have this example flow rate against the bottom hole pressure. So the instantaneous flow rate and the flowing pressure will combine together with the in a new variable, which is the normalized rate Q over dB. And this normalized rate simply will plotted against the time function or material balance time. So the resultant will be the reservoir model equivalent to the constant rate solution. So the basic comparison between pressure and rate transient analysis, the main period of interest. So in PTA, we have actual control of the well to characterize a specific phenomena, like we have a specific sequence of the test during PTA, like the isochronal test or modified isochronal or flow after flow and so on. But actually, for rate transient analysis RTA, the well is producing at actual or more reliable conditions without any control, or but even we can without a planning of the specific choke size, so we can increase or decrease the choke size during the rate transient analysis, unlike the case of pressure transient analysis. So simply, we have long build-up period and followed by this extended drawdown period. So this is the actually this is the best period for pressure transient analysis, while this is the best period for rate transient analysis. So production data analysis history, as mentioned, introduced in 1940s by the empirical Arbus equation. In this approach, you can use the flow rate only without using any bottom-up pressure data. We have three approaches, as mentioned: exponential, hyperbolic, and harmonic. In 1970s, we have Vitkovich type curve. Also, we have we will use the flow rate data only without using the bottom-up pressure data, but with the assumption we have constant BWF. But in 1980s, we have the concept of rate or transient analysis or flowing material balance and so on, which means we have variable rate and variable pressure. So in that case, we will use the flow rate and the flowing pressure data and other diagnostic plots to make complete interpretation. And most recently, we have fully integrated production data analysis using the RTA software packages like Capital IHS, Harmony, and so on. So PTA versus RTA. Applications of PTA reservoir properties like skin, reservoir mobility, fracture half length, and so on. The production efficiency and reservoir pressure, the initial or average reservoir pressure in case we have a long shut-in period. But as mentioned, we have planning of pressure transient, and the production history is very important for interpretation. But in PTA, we have high resolution and high frequency pressure data, and PTA is considered a snapshot of the well performance at specific time. But RTA simply is low resolution and low frequency pressure data, but we have long production time. So RTA representing the lumping of the entire life of the well into a complete and integrated reservoir analysis and the reservoir description. So this is a simple comparison between the constant pressure solution. As mentioned, we have constant BWF, constant flowing bottom-up flowing pressure, even during the transient or the boundary dominated flow, but constant rate, which is the major principle for PTA and RTA, we assume we're producing at constant flow rate, but the bottom-up pressure is changing with time during the transient and the boundary dominated flow period. So this is the as mentioned, we measure flow regimes: infinite acting radial flow or transient, and boundary dominated flow. So main flow regimes for the PTA, we have the infinite acting radial flow. We have the pressure difference curve and the pressure derivative, and we have homogeneous reservoir. So you will have this horizontal line representing the the infinite acting radial flow regime, which is the we have zero slope line or flat line or horizontal derivative on the log-log plot. While for RTA, the measure flow regime is the boundary dominated flow. This is the or solid state flow, as you can see. This is the log-log plot for RTA analysis. So once you have transient, so we have this shape of normalized Fisher integral and normalized Fisher integral derivative, as you can see. The measure flow regime is the boundary dominated flow characterized by this unit slope line on the log-log plot. So PTA is the high resolution, high frequency, early time data, and we have full characterization of reservoir at a short period of reservoir history, and the data range is maybe minutes or hours. The period of interest mostly build up data. Measure flow regime is the infinite acting radial flow. Analysis techniques are the traditional like Horner plot or MDH plot, the advanced or most recent technique like log-log border derivative or semilog or even specialized plots. For RTA, we have the identification of flow regime across long history of the well, estimation of fluid initially in place, and its performance-based recovery factor, and the time range may be weeks or months. The period of interest typically draw down data, and the measure flow regime is the pseudo-state or boundary dominated flow to predict the reservoir area and volume. Analysis techniques, the traditional harvest, with which the advanced technique, the log-log blessing game plot, and with material balance time or normalized rate cumulative plot. The production decline analysis simply the techniques of harvest or like the traditional technique or Vitkovich type curves. So this is the analysis tool of pressure and rate transient. So for pressure transient, we have the log-log of pressure difference and the pressure derivative. For the infinite acting or transient, we have this horizontal derivative. Similar plot of pressure against superposition time, and maybe Horner plot. But for RTE, we have this log-log plot pressure difference against material balance time, and the pressure the integral of the blessing game plot, and also normalized rate Cume plot. So one of the widely used applications or software interface are Capital, as you can see. It's an integrated platform for analyzing the low resolution, low frequency production data using the mentioned tool, and fully integrated with PTA or and fully compatible with PTA. This is the widely or the classical diagnostic the Vitkovich type curve history plot, normalized rate Cume Vitkovich type curve, and log-log plot. So log-log plot is simply a log-log of set of curves against material balance time. So we have normalized pressure integral and normalized pressure integral derivative. As mentioned, the major feature for this plot is to have a unit slope line for the boundary dominated flow data. As you can see, this is the transition between the transient and boundary dominated flow. This is the applications of log-log plot, is to predict flow regimes, and also predict the corresponding reservoir properties, specifically reservoir permeability. And for this unit slope line, we can or boundary dominated flow can predict the reservoir size or hydrocarbon initially in place. Second, plot or normalized rate versus normalized QM plot, simple relationship between this term against this and y-axis against this and x-axis, and x-axis intercept will equal the N or the stock tank oil initially in place. This is simply the normalized rate QM plot defined using this equation. The concept of all this plot is as you can see, you will have for any ratio between RE and RW, external drainage radius and wellbore radius, the using this actual the type curves on the dimensionless rate against dimensionless QM, they will have same x-axis intercept, which is the simply equivalent to the the plot of normalized rate and normalized QM plot. Also, the one of the traditional tools available are the Arbus plot. The Arbus using the Arbus equation at the abundant time, by defining specific abundant rate, you can predict the NB or the cumulative oil produced, and accordingly you can calculate the estimated ultimate recovery. Blessing more advanced decline type curve plot, as you can see. This plot is simply a replotting of the traditional Vitkovich plot, but with considering the variable flow rate and variable pressure. If you remember, in Vitkovich, we assumed we have the major assumption for Vitkovich type curve is we have constant bottom hole flowing pressure, but for this one Blessing plot, we have a new version for Vitkovich type curves, but was considering the variable flow rate and variable pressure history. This is the simply the Blessing or advanced decline type curve plot. So simply, as you can see, this plot, we have, as you can see, an x-axis material balance time, QM ratio of QM relative to Q, or fluid as function of time. But in we have three different curves. The productivity index, as you can see, Q over dB, or the pressure normalized rate. This is the BI, or productivity index. This is the first curve. Second one, the productivity index integral, defined using this equation, and also the productivity index integral derivative. So we have three different curves. This one, this is the productivity index Q over dB, and second, the productivity index integral, this one, and last one, the productivity index integral derivative in this defined in this red color, and this is the defined model to match the data. So major features for this plot, like the log plot, the boundary dominated flow, as you can see, we will exhibit a negative unit slope line on the three curves. This unit slope line and productivity index plot, productivity index integral, and BI integral derivative. This is the major feature for this plot. The second feature, the BI integral and BI integral derivative will be merged together during the boundary dominated flow period, or pseudo-steady state flow period. So the assumptions of time, rate, and the pressure data. Let's say we have changes in rate and changes in pressure against time. So we can use this data for PTA or RTA to calculate the reservoir pressure, calculate stimulated reservoir volume from RTA, and also the flowing material balance to generate the square root plot for hydraulic fracturing operations, reservoir properties, and also to predict the fluid as a function of time. So all of these applications can be performed using the data of fluid flowing pressure and time. So we have this data. Simply the basic functions is the productivity index and other normalization and smoothing of data by averaging and smoothing algorithm integration to have cumulative and also a second or first derivative to reduce the noise in the data and make the data more valid for interpretation and mathematical transformers, and maybe we have other AI algorithms to remove outliers and to match the historical performance. This is the basic rate transient analysis diagnostic plot. As you can see, we are looking for the part of the relationship that will generate, like this one, generate a linear relationship of reciprocal productivity index against material balance time, let's say, during the boundary dominated flow. Also, for this relationship, productivity index against this term on x-axis will also will have a straight line during the boundary dominated flow, which is a normalized rate QM plot. This is the x-axis intercept will be n. Also, this square root plot, as you can see, you will have this part of the term for the linear flow regime. For fracture dominated flow regime, you will have linear relationship for across the linear flow period. Also, for this one, we have this linear relationship. This is the basic approach for data diagnostics and analysis. So we have this actual data from an oil well producing from net bay thickness 8.5 meter, production time for about 1,000 hours, and this is the flowing pressure, and this is the fluid data, and this is the cumulative production in stock tank barrel. So generating log plot, as you can see, normalize the pressure and normalize the pressure derivative. So we have this model. So across this period, we have the transient. Once you have a unit slope line, which means the confirmation of boundary dominated flow, so we can predict the value of n or stock tank or initially in place. Even we can use this normalized rate cumulative plot. This is to also to have another estimation of n, which is close to 23.5 million stock tank barrel for this case. Another case for this well, it's the BI and the production time. For log plot, as you can see, this is the matching for this well. The horizontal line representing the reservoir parameter, and this unit slope line representing the boundary dominated flow or the boundary distance or reservoir size, and accordingly the reservoir volume. And we can predict the value of n or stock tank oil initially in place, estimated as 18 million stock tank barrel. This blessing game plot simply three curves as mentioned, BI integral, and BI integral derivative. The two curves of well, the three curves actually will have the negative unit slope line during the boundary dominated flow, and the pressure integral and pressure integral derivative will be merged together during the boundary dominated flow, which means another estimation of the value of a STOIP or n. See, also we have this the advanced decline analysis, or using power law exponential decline curve analysis. You can see we have also another technique to estimate the value of n at specific abundant time and specific abundant rate, and also the data is matched using the hyperbolic exponent 0.552, which is the between 0 and 1. The normalized rate QM plot, as mentioned, another estimation of oil in place, as you can see, with the x-axis intercept at time 0, at y-axis equals 0. This is the normalized rate QM plot. Now a very quick overview of hydraulic or fractured well. So reasons for fracturing operation: to have tight reservoirs, to bypass near whole pore damage, or to generate new conductive passes beyond the actual formation mobility. So you can increase the productivity and minimize the drawdown while production. This is the major applications of fracturing operation. Similarly, in hydraulic fracturing or acid fracturing, you will pump a specific fluid against the reservoir interval at high pressures, which is higher than the fracture gradient. So measure fracture parameters. As you can see, let's say we have this vertical well, and this, we have vertical fracture, and the well propagate in the direction of maximum stress in the vertical direction. So we have this fracture permeability K sub F, the fracture half length XF, and the fracture width WF, and the actual reservoir permeability is permeability K. Actually, this is the major steps for fracturing operation: to initiate fracture, propagate the fracture, and placement of proband, and finally the flowback after the complete injection of the designed proband. And this is the typical sequence of the test. After the breakdown pressure, we have the fracture abrogation pressure, and then the ISIB, instantaneous shut-in pressure, and so on. And finally, we have this pseudo-state flow after determination of the fracture closure pressure at this point. So what's important for us? We have the major flow regimes for fracture well. First, we have a fracture linear flow, which means the flow regime is linear throughout the fracture. During this flow regime, the end of the fracture is not still not reached by the pressure transient. The fracture bilinear flow, which is this one, we have linear flow across the fracture, and another linear flow from the formation near the fracture, which means we have bilinear flow. Once the fracture, the pressure transient is reached the fracture, the complete fracture half length. So we have what we call pseudo radial flow. The flow regime is going to beyond this the fracture half length, and this is the finally the formation linear, and the finally the formation linear flow at the late time, or the infinite acting radial flow. So in PTA, this is the typical response of log plot pressure difference and the pressure derivative curve. You will have as confirmation of linear flow. As you can see, according to this equation of the derivative, the slope is half. And but while the fracture bilinear flow, as you can see, the pressure difference and this is the pressure difference equation, and this is the pressure derivative will be parallel, and the slope in that case will be quarter slope, and as an indication of bilinear flow of the finite conductivity fracture. At the late time, you should have what we call the radial flow, or infinite acting radial flow. So in this example, we have the PTA log plot for this well. We have the pressure difference, as you can see, and the pressure derivative curve. The two curves are parallel, and the slope is typically half slope, showing the infinite conductivity fracture, and the model is typically matching the data on the log and semi-log plot, and this is the model results, as you can see. And this is the matching of the production history for this well, pressure and flow and gas rate against time. This is the simulated pressure matching the actual recorded pressure. But for RTA, if we have fracture type curve, as you can see, for the finite conductivity fracture. So we have bilinear flow. You will have also half the quarter slope in this plot, and also we have linear flow. We have the half slope is can see from this integral derivative, as you can see, like the Blessing plot. So this is the effect of the dimensionless fracture conductivity on the model response, but the same feature with, as you can see, we have half slope in case of the linear flow, and the quarter slope in case of bilinear flow. And this is the typical log plot in case of fractured well in RTA. We have the early time data or transient data. We have half slope for fracture linear flow, but once we have a boundary dominated flow, you will have a unit slope indication of reservoir boundary. Similarly, for Blessing plot of you have half slope at the transient data, and a negative unit slope line at the boundary dominated data. This is the data of fractured well for, as you can see, the flow rate and flowing pressure, and this is the matching for this well, and this is the decline curve plot, as you can see, using the hyperbolic decline at specific abundant rate and abundant time. This is the estimated ultimate recovery, 3.7 billion standard cubic foot. And matching of this well using the log plot in RTA, we have normalized gas potential against material balance time. This is the matching of the log plot. And for Blessing, as mentioned, matching of we have for the transit period, we have this negative half slope lines, and right here we have a negative unit slope line for indication of the boundary dominated flow. For this one, we have the what we call the normalized vacuum plot. As you can see, the x-axis intercept will be used to calculate the stock tank gas initially in place, 3.2 billion standard cubic foot. Now a quick overview of these two exercises on this this is the interface, as you can see, of Carbon Sapphire. This is the data we have, the history plot. We have the pressure against time. As you mentioned, we have in PTA, we have controlling of the fluid, and we have this last build-up period, and this is the gas rate. So back to the interpretation without going through in the QC of data and loading of data and so on, due to the time limit of this webinar, but I will go through directly to interpretation. So in log plot, as you can see, this is the unit slope line representing the wellbore storage, and we have right here this two parallel two parallel half slope line representing the fracture linear flow. We have additional feature right here in Carbon Sapphire, as you can see, in options. We can generate what we call additional derivative, which is linear derivative. So linear derivative, as you can see, will typically stabilizes across the linear flow, which is another confirmation of fracture linear flow, and this is the matching of the semi-log plot and the history plot. Additional specialized plots like to confirm the slope of the straight lines we have. So this line is the half slope line for fracture linear flow, and this one for constant Wilbur storage, which means we have unit slope line simply using this option lines. We have set of options like with different slope. So we have a slope half for linear flow of fracture, slope quarter for fracture bilinear flow, and slope one like RTA, we have solid state or closed system. So this is simply and very quickly this using PTA, but if you go to RTA using capital S, as you can see, we have this is the raw data gas rate and pressure against this, and this is the cumulative production. So, and this is the without simply and similarly without going through in the QC of data, this is the analysis tools available in Tobaz, as you can see for RTA. So this is the matching of log plot, as you can see. This is the pressure integral and pressure integral derivative, and while the transient or the early time data, we have two parallel lines of half slope presenting the fracture linear flow. And once you have boundary dominated flow, you will have complete unit slope straight line. So this is the difference between PTA and RTA. So RTA, we have long production history of the well, as you can see, maybe more than months or maybe years. So you can use all of this data for interpretation. So as you can see, we have clear signature of fracture linear flow and the clear signature of boundary dominated flow or reservoir boundary. So we can predict the estimate the hydrocarbon initially in place, and also we can predict the reservoir parameter and also the fracture parameters. For blasting game plot, as you can see for this one, and this is the matching of the data, we have pressure integral derivative, the productivity index BI, BI integral and the BI integral derivative, as you can see, and this is the matching of the model. So as the boundary dominated flow, this plot will generate the negative unit slope line. This is the first feature. Second feature, you will have merging between BI integral and BI integral derivative if you have more established and more clear boundary dominated flow. Another diagnostic tools available right here, which is the normalized vacuum plot. As you can see, once you have clear identification of boundary dominated flow, you can generate straight line to predict x-axis intercept, which is the value of hydrocarbon initially in place or gas initially in place for this example, as we have gas well. And also as this is the normalized vacuum plot. Additionally, we have this plot, which is flowing material balance plot. Also, we can use this plot to predict the gas initially in place using, as mentioned by definition of as you can see, by definition of pseudo-state constant using this plot. Q B over dq against time, so we can predict the value of pseudo-state constant B sub BSS to be used for calculations of the average reservoir pressure. Additionally, we have decline curve analysis plot like this. In this case, we have, as you can see, relationship of log Q against time, which is a semi-log plot like the traditional or the empirical Arbus equation. Accordingly, you can predict and match the historical production using the model and predict the estimated ultimate recovery. Additional tools like the specialized line plots like this one, so you can confirm the slope of the different flow regimes. As mentioned, this part we have linear flow, we have the half slope straight line, while this straight line we have unit slope representing the boundary dominated flow. Additionally, you can make a prediction of the reservoir pressure and flow rate versus time, as you can see, for long future periods. So this is simply and more quickly the applications of pressure and rate transient analysis and their applications and the major features and the common features in between, and the major principles in these two approaches widely used for analyzing the production and pressure data. That's all I have in this session. Thank you so much for